Good morning again. This is my last oral talk at this workshop, so I'm very happy, and I hope perhaps you too, I don't know. This one is on ozone again, work done as part of ESA's climate change initiative, and it's focusing on the stability of the limb and occultation profiles that are being used or considered in this project. So this work has started many years ago from the very start of the Climate Change Initiative project. So this is kind of an update of what I've been working on recently. So the whole rationale is, of course, we would like to understand whether the trends that are derived from these wonderful long-term ozone profile data sets, whether they are what the confidence level is that we have in these. So this is showing the latest and greatest result published by the Lotus team and then taken up for the WMO assessment, showing the different trends in different latitude regions at different pressure levels for different data sets. They all tend to agree, but there are some differences. Keep in mind that if you look at the mean value, when you take the mean over all data sets, trends are just 1 to 2% per decade. So that's a very high level of stability that is then required for these data sets in order to detect these data sets, to detect these trends. So these are studies done on typically level 3 data, so gridded data. This is monthly zonal mean. And if we would like to understand the cause of the differences between these data sets, we have to go back to the level 2, so individual profiles. So my first talk will be on looking at the stability of level 2 profiles, and at the end I will go to level 3. So how does it work? This is what I published a few years ago. We take a number of limb occultation ozone profile data sets, so individual profiles, and we collocate those profiles to measurements by ground-based instruments. So we use ozone sondes, we use stratospheric ozone lidars, and we use microwave radiometers. So this is a global measurement program. Some networks, like the ozone sonde network, they sample quite widely. Other networks, like the microwave radiometers, they sample at a few sites. So keep in mind that this difference in sampling is very important, especially if you would like to evaluate level 3. But for level 2, we do the collocation in space and time at every pressure level, for every single station, for every single satellite. We compute relative differences, time series of these differences, and we fit a linear slope. And this is then our estimate of the drift of satellite relative to the ground. So this is just an example for one satellite. You do this at all sites, and you plot it as a function of latitude over here at the bottom. You take the mean over all sites, and this is then the drift of the satellite relative to this particular ground-based network. So that's the whole idea. And then you run this for all satellite instruments. And this slide is on showing how confident we can be whether this is actually working. So on the left you see Aura MLS, it's an older version, version 4, and it shows the drift profile relative to the sonde network in black, the LiDAR network in blue, and then the microwave network in orange. Error bars are 2 sigma, and you can see that there's quite a good agreement, even though sondes, I use tens of sonde sites for this particular analysis. For the radiometers, I use 2 to 3 sites in this mean average. Still, results agree quantitatively. Also, the vertical structure is very much agreeing. So whenever you see a good agreement between all 3 techniques, I have good confidence that it's actually a feature of the satellite, because these 3 measurement techniques from ground-based instruments are totally independent. So this is a second example, SABRE. So I think Sean mentioned SABRE should we use Sabre for water vapor, yes or no? This is for ozone. For ozone, there's a very clear positive drift of Sabre relative to all different techniques. It's about 2 to 3%. So keep in mind the trend is just 2%. So 2 to 3% is a very limiting factor. And then at the lower end of the profile, the drift even explodes to much higher values. So if you use the data at the lower end of the profile, be careful. And even in the middle and upper stratosphere, depends on your application and your ability to correctly interpret the data and the results, whether you will use it. And this is another example that is a bit more problematic. That's the OMPS data set. This is the version retrieved by the Saskatchewan team, but using the old level 1. So there's a new version to come. So we hope that this picture, where you see a very clear positive drift in the upper part of the profile and a very positive drift in the lower part of the profile, that this will hopefully be reduced, hopefully to a sufficient level. So now I go over all results of data sets being used and considered by ESA. So considered here means that we have taken the data from the data providers. They are available to the team, and they were considered whether they would be included in the merged time series or not. So here we have a POAM on the left. This is an occultation instrument, usually by the nature of the method, where we rely on collocations, not occultations, collocations. It's a very sparse sample, so you have very large errors. So for POAM, we have 7 years of data, even though it's a sparse satellite data set and the collocations are quite sparse. We managed to see a negative drift in the around 30 kilometers. Unfortunately, at the time, there were not enough LiDARs available to confirm this. So I find it a bit sketchy to really claim POAM3 has a drift there. If you trust the sons, you have to conclude this. But it's a pity that we don't have the LiDAR there, or a completely different technique to really establish this. So SAGE 3 on ISS, this is just 2 years, so this will be updated with a new version and a longer time series. But this is what I got for the 2-year data set. It's simply not enough to constrain drift well enough. You need more time, more data. This is a number of data sets that were already part of the project for a very long time, but they have had new versions. So there's ACE-FTS, MIPAS, OSIRIS, and OMPS. And then at the bottom, we also look at Aura MLS Sabre and the SAGE 3 instrument on Meteor. I don't want to go into the details here. If you are interested in the numbers, send me an email. All of this is documented in a product validation and intercomparison report that is available on the Ozone CCI website. It may be difficult to find. I have to go back to the website, but just email me if you want to know these latest results. So what will happen in the near future is that we will use the more recent data sets and extend it in time for all of these indicated data sets indicated in red. Then, if you put everything together, so this is the drift profile of all these 14 data sets relative to SONS, relative to LiDAR, and relative to the microwave. It gives you some good impression of the state of the ability of our satellite observing system to detect trends or what their intrinsic stability is. It may give a little bit of a weird picture that results for ozone sonde are very different from those from LiDAR. So I shifted these panels up so that the altitudes match. You may have noticed this. So for ozone sondes, it seems much more scattered in the 20 to 30 kilometer range, but that's only because we have a number of instruments where we have collocations with ozone sondes, while not yet for LiDAR. So these satellites don't appear in this LiDAR graph. They would probably end up and scatter the figure more. So now, is this then enough, this method to use ground-based data to quantify drift of these instruments. Is this enough for our trend assessments? So let me first show the uncertainty of the drift estimate. So this is a 2 sigma uncertainty for drift estimate. So if you overplot and then you somehow by hand overplot typical uncertainties that are seen, that are quantified with this method, you get this picture. And if you then put this on this graph, you get about 1.5% detection threshold of drift for single sensors. When you use ozone sondes for LiDAR, it's about 2.5%. So users express their requirements, have updated their requirements. There's this GCOS document that is driving many of the activities in the field and instrument development. In terms of stability, the goal is 1% per decade, and the threshold is 3% per decade. So if you look at goal and threshold over the 15 to 35 kilometer range, we are able to verify the stability of these instruments to this level. Higher up, it's not possible. Lower down, not possible. If you then look at trends, I mentioned the trends are 2% and less, depending on altitude and latitude. It's quite difficult. But remind you, this is an analysis of single sensors. So if you combine data sets, satellite data sets, we can probably do better. And that's the second part of my talk. So how do we evaluate these level 3 data sets? Level 3 data sets is gridded. So all of the work for the assessment, or most of the work, is done by monthly zonal means. So this is a picture of ozone sonde sites as a function of latitude from top to down, and then as a function of time. Just look at the colored part of the plot, the number of measurements per month. And you can clearly see the measurement rate is quite low. Many sites measure once a month or twice a month. If you're lucky, you have a weekly measurement. But then some sites only started in the 90s, others started much earlier, etc. There are gaps. And you have good coverage perhaps in some latitude regions, but if you go to mid-southern hemisphere, it's really sparse. So how representative is this then for a monthly zonal mean? So we can't really invent information here or measurements, so we have to work with this. So what I do is that these ozone sonde data I calculate the monthly mean, take out the seasonal cycle, so to arrive at deseasonalized data. So since we have biases between these ozone sonde sites, this procedure kind of takes out the bias between sites. So then you can average all sites in a given latitude bin or longitude bin if you work with lat-long gridded data. So this is how the sonde data is converted to a level 3 style product. I haven't worked on doing this for LiDAR and for microwave yet. Obviously, if you have 8 stations or 4 stations in the network, this is very hard to get a good zonal mean, or impossible. So then you have these time series of anomalies, of sondes, so the combined network, and this is then compared to the satellite level 3, which is also an anomaly data set. This is the result for the SAGE CCI OMS data set that was used in the assessment, but we have a new release coming up, so this will be updated. But this is the result that we currently have. It's a comparison to sonde, so we are limited in altitude range to between 10 and 30 kilometers. And the result is very, very good actually. The agreement is within 1% per decade in the lower and up to the middle stratosphere. And in the lowermost stratosphere, we have a slightly larger drift of 2%, but it's not, I wouldn't say it's significant, even though that these error bars indicate this is statistically significant. In this region, it's inherently difficult to have a good quantification of errors. So probably the error bars are larger. So this is a second product, gridded product by CCI. It's latitude and longitude resolved, so rather than combining ozone zone data in larger latitude belts, we look at 10 by 20 degree lat long cells, and then do the analysis again, calculate drift with respect to the mean value for each of these cells. And then this is showing all the cells where there is an ozone zone site, but I color the ones where I have more than one site because it's, as you can see, there's a huge scatter between variation of -4 to about +7% per decade, depending on the site or the cell. So it's always better to have more than one site to cancel these effects out. So when you take the average of cells where you have more than one site, you get the dashed black line, and this indicates small trends in this altitude range. But this is very hard to have a good handle on uncertainty, so be careful by interpreting this. So we can use more data to be sure here. So I will skip these slides, and then I think my main point that I want to bring as well is it's very hard for trend assessments. We use level 3 data. It's very hard to use ground-based data to establish whether these data sets are sufficiently stable to detect small trends. So we often rely on the ensemble or the differences between satellite data sets. Now, with the looming loss of several satellites, our merged data sets will become less independent. So by definition, the agreement will become better, but not for the good reason. So this is why we definitely need this community to be to continue and have new instruments to work with. Thank you. That's it.